to properly use the cache or to design a good cache, we usually have to answer three basic questions. We know that cache is only used to store a subset of the data that exists in the main memory, and we know that usually for main memory, we're looking at a very large storage. That is, the main memory usually has a capacity larger of several gigabytes, or even tens, hundreds of gigabytes, or even terabytes of data. And the cache, however, are usually less than 32 megabyte, per processor. Therefore, the cache can only store a subset of the data that exists in the main cache. It's only a subset of the data. Cache only has a subset of the data that exists in the main cache. So when we want to access a piece of data, for example, we want to access a piece of a variable A, the first question we usually need to ask ourselves is whether this piece of data only in the main memory, or do we have a copy of this piece of data in the cache as well? So the first question we usually have to answer when we're trying to access the cache, and when we're trying to design a cache as well, is how do we know if a piece of data is in the cache or not? And then when we're able to answer this question, when we determine how to answer this question, we also need to answer two additional question at least. So if the data is in the cache, how do we find it? How do we find this piece of data? We know that cache is usually contains several cache lines, a lot of cache lines or blocks. So the variable that we're usually requesting, the data that we're requesting, usually much smaller than the cache line, or even smaller than the cache. For example, A here, if it is an integer, is only 4 megabytes. So if A is in the cache, it's probably somewhere in the middle of the cache. It's somewhere located right in the middle of the cache. So the question is, if A is in the cache, how do we find it? How do we locate it? Know that which row, which column it is in the cache, right? And if A is not in the cache, if the data is not in the cache, then we need to bring the data into the cache. The question here is then, how do we know that the data is in the main memory? So how do we bring this piece of data into the cache? How do we do this? So if it is not in the cache, how do we get it, and how do we store it in the cache? Based on these three intuitive questions, we have four more detailed and more technical questions to ask about how to use cache and how to design cache. The first question we're going to ask is about how do we know if we are going to fetch a cache line from the main memory, or if we want to locate a cache line in a piece of data in the cache, how do we know that where this cache line is going to be stored? How do we know if this cache line is going to be stored if we're going to fetch a piece of data from the main memory, or if we simply want to locate a piece of data, we want to know how do we know the cache line that contains this, where does the cache line that contains this piece of data is stored? And the hardware policy to answer this question is called cache line placement policy. It regards where do we place a particular cache line. If it is bring in from the memory, if we bring in the cache from the memory, cache line from the memory, or if we want to actually simply just locate the cache line in the cache. And the second question we usually have to ask ourselves is, how do we find a particular cache line and its related and its data in the cache? How do we find it? And the hardware policy to answer this question is called cache line identification policy. So the policy identifies cache line, so we know that what this cache line is. Usually, we're actually going to use the memory address of this cache line to identify it. The third policy we're going to ask ourselves is regards to the case when the cache is full. If we have a full cache, and we'll also bring in a new cache line into the cache, where do we store this new cache line? Apparently, because the cache is already full, to store a new piece cache line in it, we need to kick some data out. So the question here is really about which cache line that we're going to kick out so that we can replace it with the new cache line. Therefore, the policy to answer this question, the hardware policy to answer this question is called cache line replacement policy. These three questions directly corresponds to the three questions that we have asked in the previous slide. However, and besides these three questions, we also have to ask ourselves, if we're dealing with write, if we have memory accesses that are writes, are any of these policies different? Will any of these policies be different? So the hardware policy to handle write is called a write strategy, which is used specifically to handle write request to the cache. So there are four basic questions that we're going to ask ourselves when we want to use a cache and when we want to design a cache. And for the rest, the main part of the rest of this series of lectures on cache, we will discuss these three policies, the actual implementation and the actual algorithm and the implementation of these four policies. However, before we go into the discussion of the exact policies and algorithms, let's first get a basic idea of what is a cache. What is a cache? Let's learn the basic operations. Let's learn the basic components of the cache, the basic operations of the cache, and let's see one example of how cache operates. We know that, as we have discussed previously, that a cache is essentially a big array of data. It's a storage of data, which is essentially a big array of data. So this is our cache, and within the cache, we're gonna have a lot of cache lines in there constituting the element of this big array. So each row here is a cache line, and the cache line contains a fixed size of data, a chunk of data from the memory. And we have learned that the majority of the cache lines are 64 bytes in modern CPUs. However, to be able to answer the previous questions that we have asked, we cannot only store data in the cache. We also have to store some metadata, auxiliary information, to help us to identify the cache, and to help us to determine how to handle replacement policy, how to handle cache replacement, and how to handle write accesses. So instead of actually just the cache line here for each row, the actual element of each row is not simply just the 64-byte cache line. It is actually a more complex storage, which is called frame. So each row here is simply a cache line, but each row is not simply a cache line, but it is a frame. But is a component called frame, and within the frame, it has at least three components. And we have, as we have discussed, the most important part of frame is of course the data itself, the 64-byte cache line data that are going to be accessed by CPU. Besides this data, we also have something called a tag in the frame. And the tag is essentially used to identify the cache line. And we just use the memory address of the cache line to identify it. So tag is effectively the memory address of currently stored cache line. So tag is effectively just the memory address. And besides tag and data, we also have a status bit. Which is used to describe the state of this cache line. There are at least two states usually. The first state the first state indicates whether the cache line is valid or not, whether we have actually valid data in the valid cache line data in the frame. And at the beginning of the cache is empty. At the beginning of the execution of any system, the cache is going to be empty. Then the cache lines usually do not have valid data. And after a while, after we have gradually bring in the data from the memory into the cache, we then started to have valid data, valid frames and valid data in the frames. And besides valid bit, the status bits can also are also used to indicate whether the data has been written or not, or simply we say that whether the data is dirty or not, whether has been written or not. And all these informations in the frame are basically mainly used to help us to identify a cache line, or more specs, or as we usually say in the cache design, is used. This auxiliary information are used in cache line matching algorithm. And a cache line matching algorithm effectively is to find a frame to serve the correct data. Serve the requested data. If a CPU requested some data, the whole matching process is effectively to find the requested data in the cache, to find the requested in the cache in the correct frame, and then serve the requested data. So the matching process effectively does a comparison of the addresses of the requested data. So the request, remember that when we discuss tag, we mentioned that tag is effectively the memory address. So the matching process first takes the requested data, the address of requested data, address, compares it with the tag of the stored data. So this is the address of the stored cache line or stored data. And we compare these two addresses. If these two addresses match, we compare these two addresses for every frame. And if for one frame, if two addresses match, then we say that we know that we have a cache hit. We have located the data that we required in the cache. Then all we need to do is just return the proper data within the matched cache line. The cache line is 64 bytes, so we cannot return the whole cache line to the CPU. CPU is usually only requesting a part of it. So we're going to return the portion of the requested data to the cache. We're going to return the portion of the cache line that corresponds to the requested data back to the CPU. And in the case that for all the cache lines, if the requested address does not match any of the stored addresses, then we know a cache miss occurs. And in the if a cache miss occurs, we have to pick a cache line to replace, essentially. And then we're going to read the data from the main memory or higher level of caches, depends on which level of cache that we're dealing with. If we're in level 3 cache, we're going to read the data from memory. But if we're in level 1 cache, we're actually going to read data from level 2 cache first. And then after we have read the requested data, we're going to replace the victim cache line that we're actually going to replace with the requested data. And after that, we're going to return the proper rate data within the cache line. Return the proper rate data in the cache line. And this word is effectively to describe the size, is the term that we use to describe the size of data. And the word is usually 8 bytes. And when we're returning the data to the cache, when we're actually returning the data from the cache line to the CPU, we're going to return one word or several words based on the actual requested type. Next, let's look at a simple cache example. Let's look at an example of a simple cache. And here we're actually going to use a direct mapped cache. You probably don't know what direct mapped cache is. We will discuss the exact policy of direct mapped cache in the next few lectures. But for this example, this is just a simple directly mapped cache. And for directly mapped cache, all you need to know at this moment is that each cache line has a specific spot in the cache.